Diffraction. We started off last week talking about single slit diffraction, which was basically having a slit of a certain width, which sometimes is called W. I think in this case we'll call it A, so we can be consistent. That's the distance there. And what happened was we had light that travels from, say, the center of the slit to a maxima point on a screen over here. And then we have light that travels another certain distance here. And what we're looking at actually is the difference between the edge of the slit and this small part here, which is the distance y, and that distance L. And what we did in class was we had this little theta thing, looking at the angle between that. So we could say, oh, yep, tan of theta is equal to y over L. But then we also looked at, well, what is this difference between this little path length here and this path length here, L dash? And the difference is really just this small extra bit of this extra little bit here. So that is a tiny, weeny little triangle which has, I'll make it bigger because you can't see that, can you? It's delta L there. And that length here is some distance, I'm going to say halfway between A. So it's about A on 2. And you've got the angle here, which is roughly about, what's it, theta here? So small angles here. So you have that expression now, that sine of theta is equal to delta L over A on 2. And what we have is for, what was it, maxima or minima?
This is for maxima here.
This is for maxima or? Yep. Oh, no, this is for minima because it's a single slit. Let's work it out for a minima.
Oh, sorry, no, minima for single slit. Yeah.
So for a single slit, we have a minima when you have a half wavelength difference. And that's what we were talking about in class when people go, oh, I don't understand it. And we said, oh, we have this m times a half wavelength difference. And they're saying, well, what's m? M is just an integer. It's kind of like this number of wavelengths, so an integer number of wavelengths, or in our case, half wavelengths.
Yep.
So if our distance, delta L, is a integer number of wavelengths, or half wavelengths, then we can substitute into the sine theta. And that means that we end up having sine theta is equal to m lambda on 2 over A on 2. But you see that the lambdas cancel out. The 2's cancel out, sorry, not the lambda, yeah. And so you have this expression which is m lambda on A. So sine theta is equal to m lambda on A. And then we made this assumption that tan theta is approximately equal to sine theta, which means that then you can use this expression where y on L is equal to m lambda on A. But we had lots of questions about students who said, oh, well, why is tan theta equal to sine theta, and well, why are we making this assumption?
The one I do is that for very large triangles, tan theta basically equals sine theta.
Yeah.
So you can do like so you can say that.
Cover again.
Also, you can say that how does that work? Tan theta equals sine theta on cos theta. Oh. On cos theta. But then cos theta is for very, very small angles, cos theta equals approximately -1. In fact, if you look at a graph of cos theta, so this is at 0, cos theta comes up and comes down, and at the top it's basically a straight line. So in that area there, it's basically flat, and it's basically 1 over a relatively large region. So if cos theta equals 1, then tan theta equals sine theta.
Yeah. See, I use the similar expression, but looking at the graph of tan theta and sine theta. So if we go to, say, a white, and we look at sine theta in that same graph, that's your sine theta. But then what's your tan theta?
But then tan theta comes in, and it's almost exactly the same.
Yeah.
And that's what you expect in mathematics because like the same you should be able to approach the same result from the same angle. So tan theta equals sine theta
Yep, at a very small angle.
at a very small angle.
Yeah,
It's
so
like
angles
like,
less than about
yeah,
15 degrees.
should work whether you explain it from that direction or that direction.
So Mostyn's going to draw the double slit now.
So when we have a double slit, we basically have two sources of light, two separate sources of light,
but they're coherent.
Yeah, and they're coherent. So they're both emitting light that's in phase. So it starts off at the same point in a wave, and this light takes 2 points. So it takes two paths to a screen over here. And because this triangle is very long, so this slit here, we'll call that A. That's much less than a millimeter, and this length here is kind of like it's kind of about a meter in length. So if we draw a triangle there, and we'll call that a right angle triangle, we can kind of assume that these two lengths here are the same, and that this length here, delta L, is the difference in the length of these two paths here. So what we need to do to work out whether destructive or deconstructive interference is we need to count up how many waves are in each of these lines. So and these two L's here, they have the same number of lines. So we only really need to worry about the difference, this delta L here. So that delta L, if this angle in here is theta, then this angle in here is also approximately equal to theta. We can basically say it's equal to theta for the purpose of this experiment. So delta L equals A sine theta. And
that delta L is if it's for constructive, so for a maxima.
Oh yes,
your delta L is going to be an integer number of wavelengths, and for a minima, then your delta L is going to be an m plus a half. So it's got to be basically half a wavelength out, and that gives you that small description there.
Yep.
But you still have that same tan expression as well. You still have the tan of the angle being this y over big L. So that expression still holds as well, but you just have a slightly different expression here.
Yep.
But it turns out to be almost exactly the same expression. So yeah, the same expression that you come up with is if change colour again. So using that same thing, you end up with exactly the same expression, which is that the y on L is going to equal to m lambda over A, which is what we had for the single slit experiment. But in the single slit experiment, that was for a minima, whereas this one is for a maximum. And that means that you're going to have a maximum interference here for this distance y when this condition holds. And for your minimum, you'd use this here. So your minimum expression would be y on L, that distance, has to be m plus a half times the lambda over the slit width.